Welcome to Lesson 5. In this lesson, we're going to be talking all about something called z-scores. And in this particular video, I'm going to speak with you about how z-scores are what we call a score transformation. I'll talk with you very briefly about the reasons why we create z-scores and the role of z-scores in making decisions. So, just as a review, we use the mean and the standard deviation as a form of descriptive statistics. And we use one single number to describe an entire distribution of scores. So the mean is one number that describes where the scores tend to cluster, and the standard deviation is one number that describes how the scores vary on average from the mean. So these are the descriptive statistics we've been working with. They describe an entire distribution with one number. But we can also do another type of descriptive statistics where we identify a single score in a distribution. In other words, we find out maybe the address of that one particular score, where it lies in the distribution. So to do this, we're going to be using z-scores. And the purpose of the z-score is to identify and describe the exact location of every score within a distribution. Like I said, to give it an address. We know exactly where that score is in relation to the other scores. This is another function of descriptive statistics. So z-scores are similar to percentiles, but z-scores are what we call transformed scores. Percentiles are based on the raw score, but with z-scores, we take that raw score and we transform it. And the special name for this transformation is called standard scores. And standard scores convey the distance from the mean using standard deviation. So this is how we determine the address. We figure out how far away from the mean any score is in standard deviation units. So raw scores are used to calculate the mean, the standard deviation, or percentile. So we just use those scores that we collect. But a standard score is actually a raw score that's been transformed. And this allows us to make more meaningful comparisons between different groups, perhaps. It makes our numbers easier to interpret, and it allows comparisons across populations or distributions. I'm going to explain what that means in just a minute. Before I do that, though, I just want to mention to you that z-scores are used out there in the world. And here's an example of z-scores used at a cardiac center to determine whether blood vessels are within the size of blood vessels is higher or lower than normal limits. So it's used in clinical decision-making z-scores. So what you're learning now is actually something that is used. So what does that mean when we're transforming data? So we're making the data consistent and easier to work with, but when we transform data, we don't lose any of the quantitative dimension. It's not like we're changing the actual meaning of the numbers. Some common transformations that you are familiar with are Fahrenheit to Celsius. So we have a formula where we can transfer one to the other, and it doesn't change the temperature, right? It's still the same temperature. Kilograms to pounds, depending on if you're measuring yourself here in the United States or across the pond, or across the pond, I should say, then it's still the same weight, but it's just expressed differently. This is how we transform data, maybe kilometers to miles. I've run a lot of 5Ks in my life, and I happen to know that it's exactly 3.1 miles. No matter what I call it, it's always a little bit of a challenge. So we transform numbers all the time. And in fact, there was an example from lesson 4 where you transformed a number. What did you do to make something more interpretable? Think about that for a second. If you've downloaded the slides, you already know that it's standard deviation. What did we transform standard deviation from? We took the variance, which we had to use squared units, so there was a whole convoluted thing, but then we transformed it back by taking the square root of the variance to standard deviation. And that made those units back to where we started from. For example, if I were finding the standard deviation of the number of hours slept, variance would be the number of squared hours slept. But when we took the square root of it, we could go back and say variance is or standard deviation is the number of hours slept. So this is an example of when you've already made a transformation. So let's talk about a real life example with why we would want to even look at a z-score. So let's say that you received a 76 on your chemistry exam and your friend received a 76 on the physics exam. Can you compare the two of you to see who did better on the exam? Well, they're two different exams, they're two different classes, so this presents a conundrum. So what do? Is a 76 in chemistry the same as a 76 in physics? Well, what we're going to do is we're going to standardize the score. We don't know if the scores are equal because there are different tests. The scores might be different. Maybe there's more points available on one test than the other. But bottom line is, I don't know how you've scored in relation to your classmates. The location of the distribution of scores is unknown. So with more information, we can position your score in relation to the class, and we can look at your performance in relation to the class. And we do this by standardizing the score. So how do we do this? Raw scores are transformed into something called z-scores, so that the new score, the z-score, identifies the exact location of the original scores within their own larger distribution. So let's take a look at chemistry and physics again. So here we go. Both classes had the exam and the mean was 70 in both classes. So you might say, oh, well, we both did the same. If the mean was 70 and we both had a score of 76, we did the same. Well, there's something a little bit different though. We have to look also at the standard deviation. In your chemistry test, the standard deviation was 3. That means that the scores varied on average about 3 points from the mean. And so as you can see, your score of 76 is way out here in what we call the tail. This is what we call sort of an extreme score. It's pretty far out there. Let's take a look at the physics test. It had a standard deviation of 12. That means on average, the scores varied from the mean by about 12 points. That's a lot of variance, isn't it? And so when you have a lot of variance like that, a score of 76 all of a sudden isn't that extreme. So who did better on the exam? As you can see, you both had a score of 76, but the chemistry score has a much higher position. In other words, you in the chemistry class scored a lot better than most of the class, and the physics grade was more average. And so you can now compare your score with your friend's score, and you can gloat that you did better. So why is this important? Z-scores tell us the same information without us having to draw pictures of our distributions, and it provides the same information with just one number. It's really pretty cool. In the next video, I'm going to show you how to calculate a z-score. So stay tuned and I'll see you there.